What's going on, everybody? Welcome back to another video. My name is Sam, and today we're going to be talking about dynamic programming. Now, this is a topic that I see a lot of engineers struggle with. And I think one reason is that it's not really used practically in the real world. For example, I've been an engineer for a few years, and I can't really think of one time where I did use dynamic programming to solve a problem. Nonetheless, it is asked by the top companies, your Facebooks and Googles of the world are likely to ask you at least one dynamic programming problem throughout the interview process. For example, I had a phone interview with Facebook a few years ago, and the very first problem they asked me, dynamic programming. So you can do one of two things. You can either cross your fingers and pray that you don't get a DP problem, or you can take the time to sit down and actually learn it, which is what we're going to do in this video. So I'm going to be going over one problem in this video, and this for me was really the problem that helped dynamic programming stick in my mind. So first I'm going to introduce the problem. We're going to solve it using memoization, and then we're going to solve it again using tabulation. Now, memoization and tabulation are both techniques of dynamic programming, and I'll explain this in more depth as we go through the video. So before we jump into the problem, I would really appreciate it if you guys hit the like button and subscribe to the channel if you haven't. With that being said, let's go ahead and take a look at the problem. Alright, so the given problem is called minimum steps to minimize n to 1. Now we're given an integer n, and we need to return the minimum steps to minimize n to 1. So what are the steps that we can take? Well, we can either decrement n by 1. If n is divisible by 2, then we can divide n by 2. If n is divisible by 3, then we can divide n by 3. So say we have the number 10. 10 is not divisible by 3, so this is not a step that we would be able to take. Alright, and down here we have a couple of examples. So given the number 10, the answer is going to be 3 steps, because we can go from 10, we can subtract 1 to get to 9, then we can divide by 3 to get to 3, and then we can divide by 3 to get to 1. So we have 1, 2, 3 steps. Now if we're given the number 15, the answer is 4 steps, because we can divide by 3 to get to 5, subtract by 1, divide by 2, and then divide by 2 again. So the answer is going to be 1, 2, 3, 4 steps. Now the tricky part of the problem is to know which step we're going to take. Because say at the number 10, we could either subtract by 1 or we could divide by 2. So how do we know which step to take? Well, we actually don't. So we need to check all the possible steps we can take at every step. So for example, once we get to 9 here, again, we can either subtract by 1 or we can divide by 3. So at each number we get to, we have to try all 3 steps again and see which one is the minimum amount of steps that gets us to 1. So since we are trying a lot of different combinations, I'm going to go ahead and use a recursive approach. I don't know about you guys, but I'm a visual learner. So in order to actually understand how this works, I'm going to go ahead and draw a diagram before we jump into the code. So let's go ahead and do that next. Alright, so we're going to use 6 as our starting value. Now the possibilities we could go from 6 are going to be, we can subtract by 1 and get to 5, we can divide by 2 and get to 3, or we can divide by 3 and get to 2. Now if we go down to 5, we can only subtract it by 1, right? Because we can't divide by 2 and we can't divide by 3 since it won't give us an integer value. Next we go down to our 4, and if we subtract by 1, we get a 3. We can also divide by 2 and get to a 2. Now once we're at a 3, we can either subtract by 1 and get to a 2, or we can divide by 3 and get to 1. Now once we're at the 2 here, we can either subtract by 1 and get a 1, or we can divide by 2, which also gives us a 1. And once we get to a 1, we know that we're done. So if we go back up and we go to this 2, we know that we can subtract by 1, or we can divide by 2, both of which will give us a 1. So now we're done with this whole entire 5 subtree here. So now at this 3 subtree, we can either subtract by 1, which will give us a 2, or we can divide by 3, which will give us a 1. Once again, we're at this 2, we can either subtract by 1 or divide by 2. And now we're done with this subtree. Then once we get to this 2, we can either again subtract by 1 or divide by 2. So how can we use this recursion tree to actually get our answer? Well, what we can do is once we get to a 1, we know that we're done. So we can use this as our base case. So we're going to say whenever we get to a 1, we're just going to return a 0. So let me go ahead and pick a different color here. So once we get to 1, we'll say we'll return a 0. Here again, we're also returning a 0. We're going to compare and pick the minimum number here, and then we're going to add a 1 and return that value. So we're going to have basically a 0 plus 1. So this whole tree here is going to return a 1. And that makes sense, right? Because once we're at 2, it only takes 1 step to get to a 1. Now if we go to the right side here, we're going to return a 0 since we're at this 1. we're going to do a comparison. 0 is less than 1, so we're going to return a 0 plus 1. So this subtree here returns a 1. Again, if we go down this tree here, we see that we get a 1 and a 1. These are both going to return a 0. We compare those, pick the minimum, and add a 1. So it's going to be 0 plus 1. This returns a 1. Again, for this 4, we compare the 1 and the 1. They're the same, so we're going to return a 1, and then we add a 1. So this is going to return a 2 for this entire subtree here. And then for this 5, we only have one subtree, so we just take that value and then add 1 to it and return it. So this whole subtree for 5 returns a 3. Now, if we go here to this 3 and we go down to this 2, we see that this is going to be 0 and 0 again, and the whole thing is going to return a 1. The right side of this 3 is going to return a 0. 0 is less than 1, so we do 0 plus 1, and this returns a 1. And finally, if we go to the right subtree of 6, we see this 2. The 1s here are both going to return 0. Then we return the minimum, 0 plus 1. So this whole subtree here returns a 1. Finally, we do a comparison of 6's subtrees. So we see 3, 1, and 1. 1 is the minimum value, so we return 1 plus a 1. So this whole thing here is going to return a 2. And this makes sense, right? Because if we go either down this subtree here or this subtree here, it's only going to take us 2 steps to get to a 1. So that way we verify that 2 is in fact the answer that we are expecting. Okay, so now that we've actually diagrammed this whole thing out, let's go ahead and see what this would look like in code. Alright, so I went ahead and defined this method called getMinSteps, which returns an integer, and it takes in an integer as an argument. Now before we write the code, I do encourage you guys to actually pause the video and try it yourself and compare it to my answer. So the first thing that we're going to need is our base case. So we're first going to check if n is equal to 1, then remember in our diagram we were just going to return a 0, right? Then the next thing we need to do is we need to define a variable, and we'll call it result. And this is the variable that's going to hold the result of the 3 potential steps that we can take. So initially the first step we want to try is we want to try the one where we subtract by 1, because we know that we can always take that step. So we're initially going to set result equal to getMinSteps n minus 1. The next thing we need to do is we first need to check if our n is divisible by 2. So first we'll do if n mod 2 equals 0. Then we'll go ahead and recurse. So at this point we need to potentially update our result variable. So we first need to recurse on n divided by 2, but we also need to set result equal to math.min of what result currently is and what gets returned by min steps. And we also need to do the same for if n is divisible by 3. Down here we check if n mod 3 is equal to 0, then we set result equal to the math.min of result versus getMinSteps n divided by 3. So at this point we've checked all 3 potential steps that we could take, and we have the minimum value stored in our result variable. So at this point we want to return result, and then remember we were adding that 1 to result, so we're just going to return result plus 1. Alright, so let's go ahead and test this out. So initially we'll go ahead and test on the value of 6, and we're going to be expecting a 2 to get returned. So let's go ahead and run that. And we see that we do get a 2. Let's try it with another value, let's say 100. Let's go ahead and run that. We see that we get a 7, which you guys can go ahead and confirm that that is the correct number. But let's go ahead and try some larger values here. So let's try the value 1000. So let's go ahead and run that. And as we can see, this is real time, so it's still calculating. And it's going to take a few seconds. And we're still waiting. You might be able to hear my laptop's fan starting to go off. And I'm actually not sure if this is going to finish, so let's see. Okay, so it finally completed. That took about 15 seconds, and it returned the value 9. So it's returning the correct value. However, it's taking a really long time. And the higher we go with our input, it's going to grow exponentially with time. So if we go back to the diagram, we see that we're doing a lot of duplicate work here. For example, if you go down to this 2, we see that this whole 2 returns a 1, right? But then once we go down to this 2 again, we're still going down this subtree, even though we already know that the 2 is going to be returning a 1. So we see that we have it here, and then we also do duplicate work here as well as here. And again, once we go down to this 3, we see that this whole subtree here returns a 1. So when we go down here to this 3, we don't need to actually go down and do these calculations again. We already know that this 3 here is going to be returning a 1. So the current method that we have, or the current code that we wrote, does actually go down all these subtrees and does all this recalculation. That's why when we picked a really large value, it took a really long time. For this, it's only the value of 6. It's a small number, but imagine for a value like 1,000, how many times we have to do the same operations over and over again. So one thing we can do is we can use a technique called memoization, where we're basically caching our results after we see them the first time. So initially, once we get to this 3, we haven't seen it before. So we do actually have to do the calculations here, but it returns a 1. So we can keep track of that. We can say, okay, we've seen a 3 and we know that it returns a 1. So now once you get up here and you get to this 3, first you check, you say, oh, I've already seen 3 and I know that it returns a 1. So I don't need to go down these paths here. I can just say, okay, this whole thing returns a 1. And you can do that for any value that you've already seen before. So we're going to go back into our code and we're going to add a cache and see how it drastically improves the performance of our code. So if we go back into our code, we're just going to go ahead and copy getMinSteps. And we're going to change the name to getMinStepsMemo. And we're going to pass in a second argument, and it's going to be an array, and we'll just call it memo. Now the really cool thing about this is we only need to add a few lines of code to get this to work. So initially, we're just going to go ahead and first check if we've already seen memo n. And we can just check that by seeing if the value is not equal to 0. So if it's not equal to 0, we're simply just going to return whatever we have as our cached value. And then down here, when we recurse, we're just going to change it from getMinSteps to getMinStepsMemo. And we're going to go ahead and also pass that because we need that second argument. So let's go ahead and change it for the other 2 method calls. And then finally, when we get to the bottom here, we just need to update our cache value. So we just need to set memo n equal to result plus 1. And then down here, we can either keep it the same or we can just return memo n. So if we go back up to main, we're going to go ahead and change the method to getMinStepsMemo. And we're going to go ahead and pass in our cache here, which is just going to be an array of size n plus 1. So if we try this for, let's try this first for the value 6, just to verify that it still works. And it looks like we have a syntax error here with our parentheses. So let's go ahead and fix that. Okay, so if we try running that again, we see that we do get a 2, which is what we expected. But let's change our n to a really big number, like 1,000. We saw that it took about 15 seconds last time, so let's go ahead and run it. And we see that we immediately get our result. So let's try a value like 2,000. Let's go ahead and run that. And we see that, again, we immediately get a value. So I hope this really shows you guys the power of using a cache or using memoization. We look at the amount of calculations that we've reduced just by using a cache here, and clearly it's demonstrated here by the performance of our function. But there is one caveat to using this technique. Let's try a really big number. Let's try like, 10,000, which still is not that large of a number. So let's go ahead and run that. And if we look here, we see that we get this error. So if we scroll up, we see that we get a stack overflow. Now, why is this happening? And if we go back to our diagram, we see that, the method that we're using is still using recursion. When we're caching or we're using memoization, we're still recursing. So that leaves us open to the possibility of a stack overflow. And what's happening is, say we have a really big number like we use, like 10,000, we are still recursing when we're calling that -1. We're going to recurse again on 9,999. We're going to recurse again on 9,998, and so on. So we potentially have 10,000 plus recursive calls happening. And for that reason, our stack is not big enough to handle that, hence why we're getting the stack overflow. So this caching technique is great for improving performance. However, we are still vulnerable to a stack overflow. So I'm going to teach you guys a technique called tabulation. So the technique that we are currently using is called a top-down approach, where we're taking the value n here and we're basically breaking it down until we get to these ones here. The technique we're going to use for tabulation is going to be a bottom-up approach, where we start with a 1 and we build our solution up until we get to the value 6. And this will make a lot more sense once we diagram this out. All right, so for tabulation, the first thing we need to do is we need to create an array here of size n plus 1. Our n is 6, so our array will have 7 elements. We do not care about the 0 here, so we're going to go ahead and just exit out. Initially, our 1 is going to be set to 0, and this is going to be kind of like the base case that we had where we were returning 0 once we're at 1. So what we need to do is now we need to build up from 1 all the way till 6, and whatever's in 6 at the end will be our answer. So in our initial solution, we started at 6 and we subtracted by 1, divided by 2, and divided by 3. Since we're going the other way, we're now going to be adding by 1, multiplying by 2, and multiplying by 3. So initially we start at 1, and what we want to do is we want to go I plus 1 to 2. And in here, we're either going to put the value of what's in here, if there's something that exists, or the value at index I plus 1. So nothing exists in 2 currently, so it's going to be 0 plus 1. Next, we do I times 2, which will get us to 2 again. This time there is a value here, which is 1. So it's going to be the minimum of what's in here versus what's in here plus 1. Since they're both 1, we just leave it alone. Next, we do I times 3. So that's going to be whatever's in here. There's nothing in here, so we just take what's in here and add 1 to it. All right, so now our I is equal to 2. And we just do the same thing over again. We look at I plus 1, which is 3. And we either put what's in here or what's in here plus 1, and we do whatever the minimum is. So since 1 is already the minimum, we leave that alone. Next, we do 2 times 2, which is 4. There's nothing in here, so we do 1 plus 1, which gives us a 2 in here. And then finally, we do 2 times 3, which is 6. There's nothing in the index for 6, so we just do a 1 plus 1, which is going to give us a 2. Next, we go over to 3. We do 3 plus 1. We see that we have a 2 in here, so we see the minimum of 2 and 1 plus 1. So it's just going to stay as a 2. Then we do a 3 times 2. Again, 3 times 2 is 6. We see that we have a 2 in here, which is the same as what's in here plus 1, so we leave that alone. Next we go over to 4. 4 plus 1 is 5. We see that there's nothing in here, so we add 2 plus 1, which is going to give us 3. Now at this point we do 4 times 2, but that's 8, and that's not in our array, right? So we just ignore it. And again, 4 times 3 is 12, and it's greater than our n, so we ignore that as well. Next we go over to 5. 5 plus 1 is 6. So we compare 2 with 3 plus 1. 2 is less than 4, so we just leave that alone. Again, 5 times 2 and 5 times 3 is greater than the size of our array, so we just ignore that. Finally, once we get to 6, we're done, and we just return whatever is in here, which is 2, which we know from our previous examples is the right answer. So with this solution here, we can just take an iterative approach. That way we avoid any type of Stack Overflow error. And I hope this algorithm made sense. Instead of starting from the 6 and going down, we are starting from the 1 and building our array up until we get to our solution. Okay, so now that we've diagrammed it out, let's go ahead and see what the code looks like. All right, so initially we have this get min steps tab, which takes in our n as our argument. So the first thing we need to do is we need to create our table. Initially in our diagram, we didn't have any values in our array. However, in Java, when you do initialize this, it will set every index in here to 0, which we don't want. We either set it to n or a value that's greater to n. I'm just going to go ahead and set it to n initially. So the first thing we need to do is we need to set the value at 1 equal to 0, because remember this is going to be kind of like our base case. The next thing we need to do is we need to loop through our table and do those 3 calculations for each index. So the first step is going to be the I plus 1, where we set the minimum to either table at index I plus 1 or table I plus 1. The next thing we do is we check if I times 2 is less than or equal to our n, then we need to set table I times 2 equal to the minimum of table I plus 1 or table I times 2. Finally, we need to check if I times 3 is less than n, then we need to set table at index I times 3 equal to the minimum of table I plus 1, or what's already in table I times 3. All right, and the last thing we need to do is just simply return table at index n. All right, so if we go back up to main and we change this to get min steps tab, and we set this, and we remove the memo part, and let's just keep this at int n equals 10,000. So previously we did get a Stack Overflow. Now if we go ahead and run that, we see that we do get an answer of 14. So as you can see, we're not getting that Stack Overflow error anymore. The only difference is we did have to change our algorithm, whereas when we were using Memoization, our algorithm was basically the same thing. We just had to add in that cache. So that's the trade-off there with using tabulation. But I really hope that this demonstrates the power of using dynamic programming. We went from having a brute force solution where the performance grows exponentially in comparison to our input. However, when we were using memoization and tabulation, our performance did not really take a hit as the input value grew. And just within dynamic programming in general, and just kind of with everything in programming, it really takes a lot of practice to recognize these problems and to realize that you even have to use, or you're even able to use dynamic programming to solve the problem. So yeah, it really just takes practice. But other than that, that is all I wanted to demonstrate for this video. If you guys do have any questions, please let me know down in the comments section. Please like the video if you learned something. Please subscribe to my channel if you haven't. And yeah, as always, thank you guys so much for watching, and I hope you have an awesome day, and I will see you guys next time.